This is no ordinary robot. It has been specially designed to refurbish the inside of this unique cavity. It works with human control to install special heat-resistant tiles and handle modifications to the structure. Sophisticated computer programs guide the robot towards any destination on the surface. This cavity will hold hot gases at over 100 million degrees centigrade as part of one of the most ambitious research projects ever mounted. Just 15 kilometres from Oxford, Europe has come together to try to harness one of the most basic forms of energy, the energy which drives the sun itself, nuclear fusion. The project is called JET, and the JET experiment is now entering a new and exciting phase.
10, 9, 8.
For scientists, the dream of an essentially unlimited supply of energy is providing one of the great challenges as we enter the new millennium. For beneath the veil of high technology lies an almost inexhaustible energy source with built-in environmental and safety advantages. What underlies the dream is that the fuel which powers such fusion reactions derives from the elements found in water. It is the fusing together of the isotopes of hydrogen, deuterium and tritium, which releases the energy of the fusion process. Standing in the path of this glittering prize are problems of technology and science, which will draw on the ingenuity of individuals and organisations alike in the decades ahead.
One of the dome cameras and one of the mobile cameras.
Yeah.
So what we might have to do is, if we want to assemble the whole system up in the training...
These new pioneers at JET must conjure success from the use of new materials at the limits of their capabilities and the most sophisticated control systems to run every facet of the experiment. Scientists and engineers from across Europe work closely together to tackle the problems which must be solved if fusion is to become an economic source of energy. One group is using the latest laser technology to look inside the fusion chamber and measure conditions such as the temperature. The laser beams down from a roof laboratory. The alignment of laser pulses is one of many checks before the real experiment gets underway. The particle which will indicate the success of the fusion reactions is a neutron, and special detectors to count these atomic particles have been designed by another international team working at JET.
Yes, I can tell you there could be a number of reasons why.
Other teams measure emissions such as X-rays, which help to pin down the position and density of the fusion plasma. All the vast amounts of data are sorted, stored and analysed by computer specialists. The JET experiment is highly sophisticated and an adventure as exciting and focused as a space mission. The whole apparatus is now modelled in virtual reality, run from computers on the JET site. The complex jigsaw of magnets, detectors and other components can all be manipulated in virtual reality before the real designs are implemented. What lies at the heart of the JET experiment is the aim of producing a stable plasma, which is a very hot gas of particles as exists in the sun and stars. This will be used to generate energy. One approach that has gone a long way to proving itself is to constrain the plasma in a torus or donut shape. Shaped configuration. The plasma is held in place by powerful magnets. The problem is that it takes very little to destabilize the plasma. The heat and particles which emerge from the plasma need to be used or managed. In this latest phase of JET, a new device is being installed at the base of the torus cavity. It's a carefully shaped channel surfaced with special tiles, which JET scientists and engineers believe will trap exhaust products and greatly improve the performance of the machine. The JET experiment is part of a long-term effort by Europe to harness its collective talent in fusion research. For inhabitants of the Earth in 50 years' time, interest in fusion today may be no idle curiosity. For choices may have to be made on energy sources by the next generation of crucial importance to the planet.
Can you see the transformer limbs? The orange steel around, you can see part of it.
To start producing useful fusion, the scientists of tomorrow will need to reach an important milestone in managing a plasma. Containing a plasma is not enough. The temperature has to be high enough. It must be dense enough. And the energy be kept in the plasma for long enough. This hat trick is called the triple product. The target is to do this fusion hat trick well enough so that the fusion reactions become self-sustaining. This key condition is called ignition and remains the long-term aim for fusion experiments.
Japan, from the Russian Federation and from the European Union.
A central goal for JET now is to help define the physics for the next generation of experiment, expected to be a world machine called ITER.
What we foresee is a series of experiments running from 1983 when we started up to 1999, looking at the physics of plasmas that are potentially good enough for power stations. Then in ITER, we've got here 2007, but of course that's a guess. We will be looking at that ignition process that we talked about, and we'll be looking at power station technologies rather closely. And then in round about 2025, we would build, or the world would build, a demonstration power station.
To achieve these ambitious goals, the involvement of industry is vital. European expertise in fields such as aerospace, transport and special materials has already spawned link-ups with JET, which are likely to bring long-term benefits in the next stages of fusion research. One such area is the development of carbon composites. The new heat-resistant tiles inside the torus are made of this material. The French company CEP uses its aerospace experience to fabricate the composite for the tile supports or carriers. A carbon or graphite with different thermal and mechanical properties is made by Dunlop for the tiles themselves. Machining graphite is a special art, and companies in the Netherlands and Britain fashion the slabs into tiles and tile carriers. Every surface is checked, as deviations might affect the stability of the plasma. Transport is a hallmark of the Italian engineering company Ansaldo. Some of the technology they developed for JET as part of their long-term interest in fusion research has been applied in this prototype bus, which is powered by fuel cells. On site at JET, it is the deployment of skilled manpower by the engineering company GEC Alstom which helps ensure the installation of all components to specification. Throughout much of 1996, the heating and fueling systems for JET were being refined and all the detectors being prepared for what was to be the climax of over a decade of JET experiments. For the first time, The likely fuel for a future power station would be used in a major experiment, the two isotopes of hydrogen, deuterium and tritium. The clue to a successful fusion experiment lies in the behavior of a plasma at an atomic level. In a plasma, the individual particles are propelled around by their energy or temperature and the electric forces which exist between all charged particles. Usually, when two ions collide, they bounce off like billiard balls. But if the energy is high enough, they may interact or fuse.